Welcome to this lesson of chemical equilibrium about Gibbs free energy. This is a thermodynamical potential to calculate the maximum reversible work. Here we need an environment with pressure and temperature constant. This is a system with energy E that we represent as a piston. Here we have an exchange of heat, yes, Q rev. Remember, reversible. That is, it is the same as a temperature and variation of entropy. Yeah. Also, we have a variation of volume. Yeah. Remember that this can expand. So we have a pressure. I'm going to write it here. P multiplied by a variation of volume. So we have in that way. Remember the first law of thermodynamics, that energy cannot be lost or produced, just can be transformed. We have delta E, and the change of energy is the same as the transformation Q and W. What is Q? Is the heat, yeah? And W is the work. We can write this balance like this. Delta G is the same of delta E, the change of energy, minus this volume work, minus the change of heat. Take from here this part as delta H. What is this? This is the change of enthalpy. And here we have the change of entropy, and at temperature it's the same that we have here. Now we have our equation that we can apply. Go with this. Let's go with this reaction. First we need to balance. So we have here 3, this is easy, 3, and 2 here. So we have 2 nitrogens, and 6 hydrogens in each side. Find the values of delta H and delta S. We have those equations. In the first one, we have here products and reactives. This is the number of moles, N, and here, and the same for entropy. Yes, let's find it. First, delta H. What is the value? Products are here. 2 is the number of moles. 2 multiplied by this value. Yes. So we can open a bracket, 46.11 kilojoules by mole. Then what we have here, less or minus this part, reactives. So the first one to 1 mole, it's not necessary to write, but we have to see the next. The value is 0, so 1 multiplied by 0 is 0, so it is not necessary to write it. And for the next 3 multiplied by 0 is 0, so we can put just this value. So this is equal to minus 92.22 kilojoules, no more. Why no more? Because 2 is moles, yeah, so suppose here is mole, cancel those values. Delta S is the same as products. Remember how many moles? 2 moles, yeah, 2 mole Which value do we have here? This one, 192.3 joules divided by mole Kelvin. Now, minus products. Which one is the first product? Nitrogen. Yeah, nitrogen have this value, 1 mole. Remember, why 1? Because here is 1. Yes, 1 mole multiplied by which value? 191.5 joules divided by mole Kelvin. Yeah, then minus, why minus? Because it's a rate. It's here, 3 mole multiplied by 130.6. Remember the units. Let's do right here. Joules mole Kelvin. Yeah. Minus 198.7 joules divided by Kelvin. Why only joules? Remember, moles and moles are cancelled. Yeah. Now we need to convert this value to kilojoules because we have here this value. Yes. How do we do it? 1000 joules is 1 kilojoule. Cancel here and cancel here. So this is 0.198.7 kilojoules by Kelvin. We need to find is Gibbs. Remember, we have this equation. But why is this? This is a temperature. We're going to assume a temperature of 50 Celsius degrees, but we need in Kelvin. Just sum 273.15. So we're going to take 323.15 Kelvin. Now, where is the value of delta H? It is here. So let's write 2.22 kilojoules. Yeah, no more. For the next, what do we have? Plus this temperature and 23.5 Kelvin and this value. Which one? This. Minus 0.1987 kilojoules Kelvin. We can cancel here, and we can calculate our result. This is the result. Minus 156.43 kilojoules. But what does it mean? Yeah, we have a negative. This means that this reaction doesn't need an external source of energy. This reaction occurs spontaneously. Now we have finished. Thanks for watching. Subscribe for more videos.